Hello, and thanks for checking out Chemistry Connections on the Hopewell Valley Student Podcasting Network, a proud partner of hvspn.com, where students come together to publish content to share with the world. The opinions represented within this episode are those of the content creators only. Please enjoy the show.
Welcome to Chemistry Connections. My name is Daniel Wolf, and I am your host for episode number 14 called Chemistry of a Plasma Ball. Today I will be discussing plasma, electron transitions, ionization energy, and noble gases. In this segment I want to briefly overview what a plasma ball is and where it came from. Nikola Tesla, a famed scientist for his many breakthroughs in electricity, invented and patented the plasma lamp while experimenting with high voltage phenomena. In 1971, another scientist named Bill Parker would invent the modern version of the plasma ball. James Falk would later commercialize it as a novelty toy. So how does a plasma ball work? Well, in a plasma ball is a noble gas and a small electrode contained in a vacuum-sealed container. And this electrode emits a high voltage alternating current which ionizes the noble gas inside. Now this noble gas could be, any noble gas you can think of: krypton, neon, argon, most commonly neon. Even a mixture of noble gases like krypton, argon, and neon together in one container. When the gas is ionized, it becomes plasma, and the plasma is able to conduct electricity, which allows for the lightning effect seen extending from the coil to the glass. And the color of the light is dependent on which noble gas is being used. There are quite a few connections you can make to chemistry within a plasma ball. For example, the fact that plasma balls contain the fourth state of matter, plasma. When a solid is heated, it turns into a liquid. When a liquid is heated, it turns into a gas. But when a gas is heated, it turns into plasma. The ionization energy of gas is around 10,000 to 100,000 Kelvin, or 10 to 100 electron volts. Ionization energy is the energy required to remove a single electron from an atom. Plasma is formed when electrons from gas are all ionized, creating a soup of electrons and positive ions. Electricity, which is essentially a flow of electrons, collides with the atoms in a noble gas, essentially knocking off the electrons from their respective orbitals, creating plasma. And due to the fact that there is a soup of cations and electrons in a plasma, electricity can be conducted, which makes the lightning visible. And these electrons, the electrons and the cations in a plasma, are held together by electrostatic attractions. So comparing the other states of matter, solids tend to have very packed and tight-fitted particles in a last structure. It's classified by its definite shape and volume due to the fact that these particles are very tight. There's no movement between any of them. Barely any. Liquids have particles that move and slide past each other. They have more space between particles than solids, but less space than gases. And there tends to be more freedom in a liquid's movement, allowing for it to have a more indefinite shape and volume. Gases tend to have particles that move with very high speeds and kinetic energy. There's a greater amount of space between particles, which allows for even more dispersion. Plasma is very similar to gases. It has indefinite shape and volume. It even has higher kinetic energy and speed in particles due to being essentially a superheated gas. The one difference between them is that the soup of cations and electrons inside of plasma allows for the conductivity of electricity, which is very important for a plasma ball. So what are the different colors of plasma ball lightning? Well, when electricity excites the electrons in the noble gases at different orbitals, eventually these electrons are returned back to their orbitals through electrostatic attractions. They come up, then come down, they come up, they come down, and each time an electron comes down near the nucleus, a photon is emitted. This is what's called an electron transition. And you can essentially think of a photon as a particle of light, and we treat it as such. Essentially, the electron transition emits light. And this light is depending on the energy difference between two orbitals. For example, an electron transition from the third to the first energy level has a greater energy difference than an electron transition from the second to first energy level. Some examples of different colors include that neon causes a reddish-orange plasma filament effect, a lightning effect, while a mixture of neon, krypton, and xenon produces green plasma filaments. So why noble gases if you can essentially make plasma out of any gas, such as like fluorine, oxygen, or hydrogen? Well, noble gases are what are considered inert, which means they tend to be very non-reactive. This is good if you're a plasma ball maker and you have a lot of metal components inside. You don't want any of the metal components reacting with the gas inside. So noble gases have a full octet, which means they have a full electron shell. No electrons can be filled within these electron shells. That makes them very non-reactive and unable to take any more electrons from alkali metals or alkaline metals in general, essentially. I wanted to do this topic because I thought when I was young that plasma balls were one of the coolest toys back then, besides like a Power Ranger action figure or a Lego set from Ninjago. For a state of matter that makes up 99.9% of the universe, we don't see it a lot on Earth, so plasma balls gives us a glimpse into the wonders of plasma. Thank you for listening to this episode of Chemistry Connections. For more student-ran podcasts and digital content, make sure you visit www.hvspn.com.